where we're going with chapter 8. So let's just look really kind of quickly at a few things out of section 8.1. I'm going to reset my focus and hopefully get it just a little bit less fuzzy. Or maybe that's just me. Well, that's way worse. Hang on just a second. Oh, is that better? Put your glasses back on. All right, so remember, we know how to integrate a few things. We really do. We know how to integrate quite a few things, but there are some things that we have to keep in mind. Remember, I gave you a list of about 18 things or 19 things that you should know how to integrate at the beginning of Calculus 2. But if we don't have something that matches one of those forms, or sums and differences of those forms, etc., what we had to do was we had to rewrite it until we could. Now, most of the time when we see an integral that involves a fraction, then if we're going to do a u substitution, the u usually comes from the denominator, right? But one exception to that rule is if you have a natural log involved in the integral, 99 times out of 100, if there's a logarithm involved, u will be that logarithm, whether it's in the top or the bottom. Now, I said 99 times out of 100. That's not always true, but that's the first thing we try. So when we have the natural log of 3x divided by x, I would try just letting u equal the natural log of 3x, and then du would be 1 over 3x times the derivative of 3x, which is 3, times dx. So my 3's would cancel, and I would have just a 1 over x dx, which is great because I have the over x and the dx here. So this chunk right here is just my du. And so that would just be the integral of u du, which is 1/2 u squared plus c. Or in terms of our original variable of integration, that would be 1/2 the natural log of 3x quantity squared plus c. So I know we've done problems like this before, but just a reminder, when a natural log appears in the integral somewhere, most of the time that expression is going to be the u if you're using u substitution. Some other options that we talk about in section 8.1 involve when you have sums and differences in the numerator of a fraction. What if you just tried to use u equals the denominator here? Because that would be what most of us would try first, right? And then du would be 2x dx, which is great as far as I could multiply this whole numerator by 2 and reverse it with 1/2. So that would give me 1/2 2x plus 12 over x squared plus 25 dx. So this part right here would be a du, but then it's added to something else. And we can't deal with that. We can't do a du plus something in our integrand. So what might we do with this integral instead of just starting with u equals x squared plus 25? If that first method, and we could actually continue from here, but if we go, well, that's not quite exactly what I wanted to see, can we break that fraction apart? Is that legal algebraically? It is. You can break the fraction apart across addition or subtraction in the numerator and write this as x over x squared plus 25 dx plus the integral of 6 over x squared plus 25 dx. Now this one, the u substitution that I started with up here, that'd be great for that because I can just multiply by 2 and reverse it with a 1/2. And this guy's a little bit different, but it should be something we know how to integrate. Anybody want to hazard a guess there? What might it have to do with when you have a u squared plus a squared in the bottom? Inverse something. What would it be? Yes, it's an arctangent integral. Excellent. So I'm going to treat these separately. Here, I would go ahead and use that u substitution that I was trying to use on the whole problem. So I'm going to multiply this by 2 and reverse it with a 1/2. And so this part of my integral will be 1/2 the integral of du over u, where u is x squared plus 25. So that's going to be 1/2 the natural log of absolute u, or 1/2 the natural log of x squared plus 25 for just this part of that integral. Now notice I changed from absolute values to parentheses here because x squared plus 25 is already always positive, so the absolute value signs are redundant. Now I personally don't mind if you just leave them on there, but they will simplify them away if they ask you to simplify, if the argument of the logarithm is already positive. So are we good with this part? Okay, and so on this part, I'm going to look at that as an integral of du over u squared plus a squared, which, as you just said, is an arctan integral. That's 1 over a, the arctangent of u over a, plus c. Here, our u is equal to x, so du and dx are the same thing, so technically we don't even really have to do a u substitution there, but we do need to know that a would be the square root of that constant, so it's going to be 5. So we will have plus 6 times 1 over a would be 1 over 5, arctan, or if you prefer tan inverse, of u over a would be x over 5 plus c. Or we end up with this plus this as our overall answer would be 1/2 the natural log of x squared plus 25 plus 6 over 5, the arctan or tan inverse. Remember, you can use either one of these notations. It's perfectly fine, of x over 5 plus c. The key to being a good integrator is A, memorizing all your basic identities, your trig formulas, and then if it doesn't look like those integral formulas, rewrite it until the pieces do. And so we just really used our basic integral forms here. We just had to separate the fraction to be able to do so. Any questions about that one so far? Well, that one at all, because we're done. All right, that was a heartfelt sigh. Are you sure you don't have any questions? That's okay. That's okay. All right. So what about this guy? This is another one of those that we just looked at. If we just had the 8x on top, we would just do a straight u substitution. du over u to the 1/2, basically. If we just had the 2 on top, that would be an arcsine integral. But since they're added to each other, or one subtracted from the other, on this one, we would need to integrate by separating first. So I'm going to rewrite that as the integral of 2 over the square root of 1 minus 4x squared dx minus the integral of 8x over the square root of 1 minus 4x squared dx. Now remember, you can separate across addition or subtraction in the numerator, but not the denominator. So I'm going to do different methods of integration on these two parts. Here, this is also an inverse trig integral, but instead of being an arctangent, it's an arcsine. So we would have, this one is of the form the integral of du over the square root of a squared minus u squared. In general, those integrals are arcsine of u over a plus c. Now notice, for this particular inverse trig integral, there was no 1 over a out front. Basically, in the derivation of it, the 1 over a canceled with an a. And in this one, we're just going to do a straight u substitution. So if I'm trying to do the arcsine formula here, I need to identify what's my a and what's my u. A will just be the square root of this constant, and we're going to go with the positive square root always, just for ease, and it's just our kind of normally accepted square root there. So what about this guy? What's the square root of 4x squared? We're going to take the non-negative square root there, or what we would consider to be just the simplest one we can think of. So we will have, if u is equal to 2x, then du would be 2 dx. This part right here is what people very often forget when they're doing substitutions with inverse trig integrals. You've still got to follow that u substitution through, or you will miss the coefficient out front. So for this particular part, this would be right here, that's just our du, so that would be du over the square root of a squared minus u squared, which is arcsine of u over a would be 2x over 1. Or you could write it as just 2x. I just put the 1 in for emphasis that it is u over a. Then I'm going to integrate this part using a different substitution. We would be letting u equal 1 minus 4x squared there. So du will be negative 8x dx. So when I multiply by negative to get a negative 8x in there and reverse it with a negative out front, that will end up with a plus between those two integrals. So I will have plus the integral of du over u to the 1/2. Now, give everybody a chance to catch up with me there and let me know, do you have any questions about that part? So we're all good so far? All right, now if it bothers you to have a u substitution here and a u substitution here that are not related to each other, you're welcome to use like a w or a different variable over here. But these are two completely separate u substitutions on this problem. So that would be, let's see, the integral of u to the negative 1/2 du is u to the positive 1/2 times 2. So we will have the arc sine of 2x plus 2 times u to the 1/2 will be 1 minus 4x squared to the 1/2, and then we just put our plus c on at the end, rather than just having a plus c and then another plus c. We typically just add one arbitrary constant at the end. We still okay? All right. What about this guy? Well, here we have a trig function in the bottom, and most of the time our first guess is to just let u be 1 minus the cosine of 7x. In other words, what's in the denominator. The problem with that is if I do that, I'm going to need a sine of 7x in the numerator to give me my du. Now, I could multiply by the sine of 7x up there, and that would be fine, but then I would also have to reverse it with a sine of 7x in the denominator. And since I'm using my, or I'm multiplying by something that involves the variable of integration, I could not multiply by that outside. And so I could make myself a du up here, but that just introduces an extra sign that I don't have anything to do with. I don't have anywhere to go with it in this u substitution. So this u substitution might not work in this case. So we go back and we say, okay, what else could we do? Well, I know trig identities are y'all's absolute favorites, but one of the things that you particularly need to think about is how can you rewrite this so that maybe we can do a u substitution on it or something like that. Since it's a cosine, there's really not a whole lot we can do with that part, right? Now, if it had been a tangent, we could rewrite it as sine over cosine or something like that, but when it's either a sine or a cosine, that's probably not going to be an option. So what we're going to do is try an algebraic trick here where we multiply top and bottom by the conjugate of the denominator, as far as it's just the same terms with the opposite sign in the middle. And you go, why in the world would I want to do that? Well, let's just see. If we multiply the denominator out, we would have 1 plus cosine of 7x minus cosine of 7x when we multiply the outer and the inner terms together, minus cosine squared 7x. And then I'm going to go ahead and factor that 63 out front. So I have 63 times the integral of 1 plus cosine of 7x over 1 minus cosine squared of 7x dx. And so right now it looks worse than it did when I started. But what is another way we could write 1 minus the cosine squared of something? Well, remember, we have the Pythagorean identity for sine and cosine. We know that sine squared x plus cosine squared x is equal to 1 for any x value. So 1 minus cosine squared x is equal to sine squared x. So I could replace this 1 minus cosine squared x with, or pardon me, 1 minus cosine squared 7x with sine squared 7x from the Pythagorean identity. Okay. That's a fairly, I don't want to say common, but it's not uncommon either, trick when you have something like a 1 minus sine x, 1 minus cosine x, 1 plus tangent x, or something like that, that you can't deal with kind of in a straightforward u substitution. Now, I'm still going to need to break this apart. That would be the 63 times the integral of 1 over sine squared 7x dx plus the integral of cosine of 7x over sine squared 7x dx. So we have 63 times the integral of, what is another way you can say 1 divided by sine squared? It can be written as what? What's the reciprocal function of sine? Co-something. You're close. It's cosecant. Remember, 1 over sine is the same thing as cosecant. So this would be cosecant squared 7x dx plus the integral of cosine of 7x over sine squared 7x. Now, why did I rewrite that? Well, if I tried to let u just be sine of 7x here, then du would be a cosine of 7x, and I don't have a cosine in this part. So I just rewrote the sine squared using a trig identity. So here, this integral, whose derivative is cosecant squared? It's negative cotangent. So I'm going to have a 63 times the integral of cosecant squared 7x is negative 1/7 cotangent of 7x. And then for this part, I'm going to let u equal sine of 7x. So du will be 7 cosine of 7x du. Or 7 cosine x dx, sorry. So I'm going to multiply this part by a 7 and reverse it with a 1/7. So I will have plus 1/7 the integral of du over u squared, where u is that sine of 7x. So we would end with 63 times negative 1/7 cotangent of 7x plus the integral of u to the negative 2 du is negative 1u to the negative 1, or negative 1 over u, which in this case, since I've run out of paper, I'm going to go ahead and erase that and put in what u was in terms of x. That would be a negative 1 over sine of 7x, and then plus c. And of course you could go ahead and multiply through by the 63 times negative 1/7 and get negative 9 cotangent of 7x minus 9 over sine 7x. And you could, I mean, the calculus part is done there, right? But if you wanted to simplify it trigonometrically, you could rewrite that as I mentioned, negative 9 cotan of 7x. 63 times 7 times negative 1 is negative 9 over sine of 7x plus c. Most of the time they won't leave a sine 7x just alone in the denominator of a fraction. They would probably rewrite that as cosecant 7x. Me, I wouldn't care. Either way would be fine. Questions? Here? Yeah, the integral of du over u squared was the integral of u to the negative 2 is negative u to the negative 1, so that's where I got negative 1 over u, and I just replaced the u with sine of 7x for that part. Did that answer your question? Okay. It's been a while. You're in it to win it now, so you know, let's just go forward. And pretty much all we do in chapter 8 is integration. Well, you don't have to memorize all the trig identities, but those that I told y'all, you know, way back when, that you probably needed to know, yeah, you're going to need to know those. So, and remember, let me see if I have a book somewhere. That would be so fantastic. Okay. I know some of you may not have a hard copy of your textbook, and that's okay, but if you do, remember, these are also, I think, in the e-book as well. But if you look at the back of the front page of your book, the identities that we will use the most are the reciprocal identities, the Pythagorean identities, the double angle and half angle identities. And I purposefully omitted the tangent of 2 theta. That's not an identity that we use as far as integration techniques are concerned. But these, yeah, you really do need to know them. We don't typically use the sign identities much, the plus or minus sign, I mean. All right, and not all of them will come down to a trig identity or anything like that. I just wanted you to be to show you one where we had to do a weird kind of multiplication for a trig integral, because those do pop up, and as is evidenced by your question, yeah, they kind of freak people out a little bit. So we'll get better at them, though. You will. You will. All right. So here's a different kind of thing. Any suggestions as to how we might rewrite that? Or do we even need to rewrite it? Could we just use a straight U substitution? Correct. So why? If you chose U to be e to the 2x plus 4 e to the x plus 4, then du would be 2 e to the 2x plus 4 e to the x dx. And we look at that and go, well, that's just way too much stuff. I don't have near that much stuff up in the numerator, so I can't really use that. So we go back here and we go, okay, well, is there any way I could rewrite this that I could use a U substitution? How about factoring that denominator? Remember, e to the 2x is e to the x squared. This is plus 4e to the x plus 4. So you could factor that into e to the x plus 2 times e to the x plus 2. Or that's the integral of e to the x over e to the x plus 2 all squared. Now can we do a straight U substitution? Why, yes we can. If we just let u equal e to the x plus 2, then du would be e to the x dx, and this would be the integral of du over u squared. Or remember, that's the same thing as u to the minus 2 du, and the integral of u to the minus 2 du is minus u to the minus 1 plus c. Same integral part that we had on the previous problem as far as the integral of u to the minus 2, but it's just we have a different u. So some things that you can do, guys. You can break apart a fraction across addition or subtraction in the numerator. You might try multiplying by 1 in some very specific way, like we did in the last trig value function. Or you might try factoring something. These are just a few of the different ways that we can rewrite a function so that we can bring it back to something we know how to integrate. And it's kind of different in section 8.1 because there's just kind of this variety of different methods to rewrite. And the rest of chapter 8, we're going to be looking specifically at one technique per section. So we'll have a particular method of getting it to an integral that we know how to integrate in section 8.2, and then a different method in 8.3, and so on and so forth. But before we go on, do you have any questions about this particular problem? Yes.